I found first from that, but this is the way they should be presented after all. So I will start with very small brief introduction, following by I will explain what are quantum dots in peptide structures, and then I will show how those peptide structures have special symmetry that allow us to observe these two phenomena. And I will skip to a phase transition from these quantum dots to quantum world structures in those exactly peptide nanostructures, and will conclude with quantum confinement in quantums. So let's start. And the story starts at Udi Gadik's laboratory in 2003 when he established all of the nano research. And Udi is working with amyloid proteins. Amyloid proteins are the proteins that causing some diseases like the Parkinson's disease, the Alzheimer's disease. So he's trying to find an inhibitor to those diseases, and trying to think how to block the formation of some structures that cause the diseases. So we're working a lot with Alzheimer's disease, and this is a protein called amyloid beta, which is one of the main causes for Alzheimer's in humans. And he found these small 2 amino acids in the middle of the sequence of the A beta protein that if we take this small peptide, which composed only from 2 phenylalanine residues, we can form a lot of nice structures. And that started with nanosections. So we can form peptide nanostructures that just line on the surface. We can make them stand. We can make them be spheres. We can make them be like spaghetti-like structures, and also something like nano ribbons that will be different from that peptide nanostructures. And as part of the laboratory, I was working about the properties of these structures, and I was studying the optoelectronic properties. And let's skip to the results section. So one of the basic measurements we can do with optical electronic structures is to do absorption spectrum. This is the regular absorption spectrum of these spaghetti-like structures. And I found right in the beginning a little bit interesting phenomena. You can see here 2 graphs. This is the same material. This is I'm using the same powder from this to this graph and this graph, but this is in low concentration, this is in high concentration. And in low concentration, I cannot get those structures, and in high concentration, I can get these structures. And I see this graph is different. The monomer absorption spectrum is this wide one, but suddenly I can see this small peak, chukchik. And this chukchik is enhanced as the structures are forming, and this peak is disappearing. So what is this chukchik? So this is let us think about semiconductors, because in semiconductors we can find very similar absorption spectrum. As you can see here, this is the absorption spectrum of quantum dots, which is very similar to this peak. And if I can compare quantum dots to normal organic dye, I can see that quantum dots have this small peak at the red edge of the absorption spectrum, and the organic dye is a wide absorption spectrum, as we can see it belongs to the monomer. So that led us to the theory. Maybe we have in these structures a quantum dot-like structures, but to know that this is quantum dot structures, we need to take it. We need to see the crystal structures. We need to maybe to break the structure to see the quantum dots. And we know that quantum dots also create something that's called excitons. Excitons are a pair of electrons and hole. When you excite the electron in hole, the electron moves up, but because it's quantum dot, it's confinement in all 3 dimensions, it cannot move. So we've got a strong connection between the electron and hole. So to find the exciton, we use the PLE. It's photoluminescent excitation. And we can see a big shift in the PLE spectrum of the structures as the structures are formed in organic dyes, but as the concentration is being increased, so as the supposedly quantum dot structures is being formed, we receive very, very narrow excitation peak. This full width at half maximum is less than 4 nanometers, which is very low. And this proves me that I have an exciton here. This is a characteristic of highly crystalline structure. I can follow the dynamic of the exciton as the spaghetti-like structures are being formed, and I can see that as the fibrils are being formed, I can see the rise of this exciton peak and the decrease in the full width at half maximum. As we can see here, this is the intensity of the exciton peak, and this is the decrease in the full width at half maximum. So we published that, and that maybe lots of reviewers told us that if you're saying it's quantum dots, we want to see them. So actually, it's a little bit difficult to break them because they really like to be in a tube structures. But we can break them either by using a very acid or very basic solution or in organic solution. So I broke them and went to the AFM because I cannot use SEM anymore. And, well, I can see the quantum dots. And how the quantum dot structures are quite unanimously. They all have around 2 nanometers in height. And this process is reversible. I can break these tubes to the quantum dot structures, and I can also take the quantum dot solution and make the tubes. It's all a matter of pH or a matter of just transferring it from aqueous solution to organic solution. And we also made some sort of theoretical calculation. We can find from the optical, the PLE, and the absorption spectrum, we can find the exciton binding energy, and from the binding energy of the exciton, we can use the common quantum dot theoretical calculation to calculate the size of the quantum dots. And I don't give the equations here. I didn't think it's appropriate to this form, but by using this calculation, we can calculate the size of the quantum dot to be 1.65 nanometer, which is quite in good with AFM pictures. So how do I know that these dots are the quantum dots? Because they have the same crystal structures. I went to the XRD with one with the quantum dot solution, one for the peptide nanotube solution, and I receive an identical X-ray. And also the PLE of the dot at high concentration and the PLE of the dissolved peptide nanotubes is the same. So I'm quite sure that those structures are actually the elementary quantum dot structure of the peptide nanotubes. And also the guys from Nature thought it's important enough to be on their news and views and declare that as peptides biological semiconductors. It was nice to see that. So next, those peptide nanostructures have highly crystalline structure, as you've seen in the previous slide. They have p61 non-centrosymmetric hexagonal space groups. So among the 32 space groups, 20 of them are non-centrosymmetrical, and one of them is this p61. So the non-centrosymmetrical space groups should have several properties. So we decided to follow 2 of these properties. The first one is nonlinear optics, and the second one is piezoelectricity. So let's start with the first one, nonlinear optics, and we focused on second harmonic generation, which second harmonic generation is if we excite in a certain wavelength the molecule, so the frequency is doubled, and if we excite in 800 nanometers, we will receive a sharp peak at 400 nanometers. And this is exactly what we got. We took a titanium sapphire laser, and we excited the peptide nanotubes at 800 nanometers, and we receive a sharp peak at 400 nanometers. This peak is got a quadruplex behavior according to the laser intensity, as normal second harmonic generation crystal should have. And another interesting phenomenon, we got also this small peak. this small peak is not second harmonic generation because it's not doubling the frequency, but it's 2 photon luminescence because we excite here and we receive it here. So it must be 2 photon. And we found interesting phenomena with this peak. Let's be honest, it's not easy to observe it, but in some cases, we observe a threshold. What do I mean in threshold? I mean that when we increase the laser, the titanium sapphire laser intensity, it acts like a normal second harmonic generation should act, but in some laser intensity, the signal just bursts, and we can see it even, you just see flashes on the surface. I will show you in the next slide. So from doubling the frequency, we get 7 times the intensity. So it was very surprising, and we can see also the directionality of this peak, meaning it's not all over the place. It's got the directionality, and you can see it in this picture. This is before the threshold. You can see a small dot here, and this is after the threshold. We can just see the directionality of the emission, and this is one of the steps to maybe a lasing. It's reversible, but the problem that we see, it's sometimes to get this, we are burning the sample because we need a high intensity laser. So this is the reason that we cannot see it in many cases, only in very rare cases, because usually it burned in this state. But when it's reversible. The answer is yes. In the cases it doesn't burn. So let's skip to the second phenomenon. The second phenomenon is piezoelectricity. What is piezoelectricity? Is that when you applied an electric field to a crystal, to a non-central symmetric crystal, you cause strain in the crystal, so you can change the dimension of the crystal structure according to the voltage, and it's also reversible. You can cause a strain and then produce electricity. So the most used techniques as for today to measure piezoelectricity in the nanoscale is with AFM. AFM has big advantages because you can make this AFM tip conductive. You can plug it to an electric source and just play with it. And so we apply electric field between the AFM tip and the gold surface. All the nanotubes are attached to the gold surface, and we measure. According to the tensor of the P61 space group of the peptide nanotubes, we should measure it on standing tubes. But we really cannot measure it on standing tube because they will always fall. They will never be stiff enough to get an AFM tip press on that, and they will just bend and they cannot make the measurement. So we have to measure it lying on the tube. But it's still good because if I'm applying an electric field on that direction of the tube, according to the tensor, if the spontaneous polarization vector of the tube is along the tube axis, so if I apply voltage in this direction, the tube should move in this direction. This is what the crystal structures tells us. So we apply an electric field here. The tube is moving like this, so the AFM tip is just twisting. And we can measure how strong the AFM tip twists, and this tells us how strong the piezoelectricity is. And we can calculate the piezoelectric tensor. So at first, we measure in plane is the tube moving in this direction and the AFM tip is moving like this. And out of plane is if I apply electric field like this and the tube suddenly widen. So this is out of plane, but according to the tensor of the tube, it should not go in this direction. It should only go in this direction. So this is exactly what we got. Out of plane, we got no signal at all. That's okay. In plate, we got two types of signal, one bright and one dark. And this is just by accident because some of the tubes, when we spill them on the surface and connect them, so one will have a spontaneous polarization in that one, and the other one will have a spontaneous polarization in the other way. And to check it, it's very, very easy. We just move the FM tip. We physically rotated the sample, so all the tubes that were that way is just now like that, and vice versa. And this is exactly what we get. And all the bright tubes become dark, all the dark become white also in this when we reverse it. So it ensures us that this is piezoelectricity, and we can flip it, so it's good. So we wanted to know how strong is the piezoelectricity, so the most common is just to compare it to common crystals, because common crystals like lithium niobate has been studied in the last 30, 40, I don't know how many years. They're piezoelectricity, ferroelectricity, all the dielectric-related phenomena, and we know that the piezo tensor of those crystals, and it's comparable. It's not like if we take organic piezo crystals like collagen. Collagen have piezo, but it's like 10 or 20 times less this peptide nanotubes. So as for today, this is the strongest piezoelectricity that's been observed in bio-inspired structures. So let's move forward. So I talked about peptide nanotubes that have sort of quantum dot structures, and this quantum dot is non-centrosymmetric, so it has piezoelectricity, it has a second harmonic generation, and most probably other phenomena like third harmonic generation, also pyroelectricity, but I didn't have time to explore all of them. But we noticed an interesting phenomenon. We know today to use the same powder as I make in the peptide nanotube solution, but if we put them in a vacuum chamber and we heat them, they can make a surface, rather unanimously surface, which looks a little bit different than the normal peptide nanotubes. It looks like ribbons, like you see here. And these structures, it's very different. It's got very different properties than the common peptide nanotubes. So this is the powder, and suddenly we receive an optical absorption of steps, very long, up to 500 nanometers. And it made us think, what is this step-like optical absorption? And this is a slide from a solid-state course, and we went again to quantum confinement. And we know if this is the density of states of a bulk, density of state meaning the statistical of the electron to be in a certain energy, when we confine it in one dimension, meaning the electron can move in 2D, the density of states is step-like, and the optical absorption should behave exactly like the density of state of the materials. And indeed, we see a step-like optical absorption. So also, it's got different optical absorption spectrum, and it got also different photoluminescence properties. So the photoluminescence of the exciton of the quantum dot is in the UV. But suddenly, in here, we can see also a strong photoluminescence in the blue region. And the origin, this is the photoluminescent excitation of this blue luminescence, is coming mainly from the second step, and part of it comes from the first step. This is at the same places of the steps. So we thought to ourselves, we've got a new structures which should behave like quantum wells, and we got a new and exciting luminescence, so let's try to see it. So we can see it. This is photos from fluorescence microscopy. And the nice thing in this vapor deposition process that we can control the thickness of the structures, when we can control the density, we can heat it less, we can heat it more. And so I can control it from, this is like 4 or 5 micrometers. And this is very long, this is 30 micrometers. So I can control the luminescence of the surface, and as I increase the thickness, I can increase the photoluminescence. And also we can do patterning, because it's a solid-state device. It's not in a solution. We can use hard mask and just evaporate it through the holes, and we can do a blue patterning of the structures. So we thought to ourselves, why this is blue, and why this is in UV, why this is quantum dots, and why this acts like quantum wells. So we decided to go to the quantum dot structures and thought to ourselves, what are we doing in this vapor deposition? We just heat them. So let's heat this quantum dot and let's see what's going on. So this is what we got. So we heat it, and we noticed that from a linear FF, this molecule can cyclist. You can see this dicarboxyl, this is the amine, just closing on each other and become cyclo-FF. In chemistry, this is called decatopiperazine. And this is Toff-Sims analysis that confirm our hypothesis. This is the molecular weight of the linear FF. This is the molecular weight of the cyclic FF. And we can see also here in TGA that around 150 we got some sort of phase transition. So what is this phase transition? It's altering almost every aspect of the properties of the peptide nanotubes. Let's start with the morphology. This is the peptide nanotubes. You can see a hole in the middle. It's hollowed. So we started to heat it with E-beam. This is taken in a stem. So after a few seconds, this hole is just closing. And you can see when we zoom out, this is the heated area, this is the non-heated area. And we can see here, this is closed tubes, this is open tubes. We can make them stand and follow a little bit the closing of the tubes. And as we heat, the tube is gradually closed. I didn't bring the movie, so don't worry. But the most interesting part is the crystal structures is completely different. From a P61 non-centrosymmetric crystal structures, we are moving to a centrosymmetric crystal structure. This is the crystal structures of the thermal-induced peptide nanotubes, and this is PNMA. So if we move into a centrosymmetric, all the piezoelectricity, the second harmonic generation should disappear, and they disappear completely. This is the signal of the native. This is the thermal-induced, no second harmonic generation. And also, this is the piezoelectric signal as a function of the bias. And in piezo crystal, this is a linear relation. As we increase the bias, so as the piezo signal is being increased. And this is of the native tubes, and this is the thermal-induced. No piezoelectricity, no second harmonic generation. This is because they are centrosymmetric. And also, the optical properties has changed from this peak-like optical absorption to a step, from a UV luminescence to a blue luminescence, from one source to two steps. And the nice things here that we can really see the peptide nanotubes blue. And this is intrinsic color. It's not, it's without dye. This is the peptide nanotubes themselves. So they are blue. So let us finish with going back to the beginning. As I told you, Udi started this nanotechnology field because he was studying amyloid proteins. So I thought to myself, if the core recognition motif of the amyloid proteins have quantum confinement, maybe the amyloid protein itself has quantum confinement. So I worked at the beginning with insulin because it's very cheap and very easy to work with. And insulin can form amyloid fibrils. And indeed, I can see a concentration-dependent PLE spectrum of the insulin fibrils moving from a normal excitation spectrum of the insulin to a very narrow exciton-like photoluminescent excitation. Also, the structures of the insulin. This is, I'm talking about, I'm not waiting several hours to make the fibrils. So this is just by increasing the concentration and pushing the monomers to crystallize in a way. Also, the crystal structures is very concentration dependent. And I suspect, this is only my hypothesis, that the FF motif of insulin is crystallized in a similar way as the quantum dots of the peptide nanostructures. This is, I highlight the FF motif of the insulin, and we can see it, it's really in close proximity in the PDB file of the insulin. And this is really nice, because if I can follow the crystalline but simple PLE measurements, maybe I can design a way of measuring inhibitors to amyloid proteins just by putting 10 seconds measurements in spectrophotoluminescence. And so I'm using insulin, and we know that there is a molecule called epigallocatechin chalat, or EGCG, the acronym of it, and it inhibits fibril structures of insulin. When I added it, I cannot see insulin. So I checked if the photoluminescent excitation is changing as a function of adding the inhibitor of insulin, and indeed it does. When I use different concentration of the inhibitor, I can get different PLE structures. And I use the same insulin concentration, but different concentration of the inhibitor, and you can see a gradual change of the PLE spectrum. So I can really do dose-dependent of the inhibitor to the amyloid fibril by simple spectroscopic measurement. And maybe even we can do I didn't get to that point, but maybe you can do detection of very early stages of crystallization of amyloid proteins with simple spectroscopic measurement. And by that, I want to conclude. I want to thank both of my Professor Udi Gazit from biology, Professor Gil Rosenman from electrical engineering, and because this interesting involvement I could get to this interesting subject, I believe it's interesting, and all of our very wide collaborations. And I will finish my PhD very soon. I want to thank the nano community of Tel Aviv University, which is really a great community. It was a pleasure for me to be here in the last years, and of course you. Thank you.
Okay, questions please. David?
Beautiful work.
Thank you.
How many dipeptides do you have in a single quantum dot?
We suspect we have only 2 dipeptides, like 4 aromatic rings, and we've done also TOF sims of that and mass spec of that, and always we receive the structures, the molecular structure that correspond to 2 dipeptides.
So actually that leads me to the next question. So if I want to encode, let's say, to add a tag to a protein, could I encode multiple dipeptides and generate little quantum dots, essentially attached that genetically, right, attached to the protein of interest, just like we do with fluorescent protein? Can we use that as a genetically encoded tag?
I had this question many times before. I think that no, because they are not that stable. They are concentrated dependent. When they are in tube, they are perfectly stable. It's really difficult to dissolve it. But when they are tubes, they are not strong enough, and they can be formed and deformed. It's not. Yeah, I understand, but it's not like semiconductor quantum dots, which are single crystals. It's the crystalline is it's forming because of this self-assembly stuff, but it also can be a part. So I will not do a labeling according to this quantum dot, and also this the light in the UV, which it's maybe difficult to see.
More questions? Yes, Gil.
I think that the term quantum dots or quantum confinement is a bit misleading, because I mean the exciton in your system is very different from the exciton in a semiconductor.
I agree.
It's already confined to a molecule, so it's just the coupling, the pi-pi coupling, that gives you the changing the optical properties. So it's more about the pi-pi interaction rather than finite size effect. And you probably don't have also.
I completely agree. That's why I'm always careful to say quantum dot. I always say like quantum dots, and I totally agree with you.
The concept of quantum dot was there. The concept of excimer was there, which is exactly this one. That you can excite the monomer, and then the dimer forms a superposition of excited and ground state species. Malikan got for that and other things his Nobel Prize, but that was probably before I don't know what's your age. So the concept is there. I think you should refer to that and see. Maybe it's not this, but the concept that you have crystals that then spoil the symmetry and form dimers of excitation which can propagate and can have then stimulated emission, whatever you want is there in the...
Yeah. Okay, I'm familiar with it.
Okay, if there are, oh yes, there's one more question.
If you apply different equations to calculate diameter from the exciton energy, or you need to know something regarding other, like the electric constant, or
there are some parameters that we have to guess in this point, like the refractive index of the molecules, which we assume it's rather similar to the one of benzene, because there's aromatic structures. The type of the exciton, which we assume is Frenkel, because the higher binding energy of the structures. And of course, it needs more theoretical hard work that to calculate. Some parameters in our questions we had to guess, because we don't have a clue what are those parameters. But I really think that the guesses are more or less will be around the actual value of it.
you cannot apply inorganic quantum dots formalism to this structure to calculate the diameter from the energy. It's not the exact type of, it's not the exact same type of...
Yeah, I understand, but okay, I agree with you, but this is the best what can be done now, I think. But I totally agree with you that we need maybe to set a new equation type to this kind of structures.
Okay, thank you, Nadav.
Thank you.
So we